My goal here is to cover a big chunk of thermodynamics, and perhaps I've bit off a little more than I can chew in one video, but we'll see how it goes. The first thing I want to show is that PV equals 2/3 times N times LKE bar. Here, N is the number of molecules in a gas, is the number of molecules in a gas of volume V. And LKE bar is the average linear kinetic energy per molecule. And P is the pressure within the gas. If you have a gas composed entirely of one type of molecule, you can break that linear kinetic energy down into 1/2 mv squared bar, which is the mean of the square of the velocity of those particles of mass m. Let's note here that the number of particles, capital N, times the mass m, is the same as the number of moles per particle, lowercase n, times the mass per mole, mu. With that change, we can relate this expression to the most familiar form of the ideal gas law, PV equals nRT. A less familiar way to express it is to say that PV equals n k sub b t, where k sub b is Boltzmann's constant, which is the ideal gas constant divided by Avogadro's number. Let's see if I can describe one more relation to put this equation into context. You may be familiar with an equation saying delta U equals n c sub v delta t. That is, the change in internal energy of n moles of a gas equals n times the specific heat at constant volume times the change in temperature. In the case of a monatomic ideal gas, the internal energy of the gas is composed entirely of its linear kinetic energy. By contrast, diatomic gases also have rotational kinetic energy. Correction, let's remove that average sign and put in a delta LKE. For a monatomic ideal gas, we can conclude that the molar specific heat at constant volume, C sub V, is 3/2 R. The linear kinetic energy and the internal energy are the same. But what changes for diatomic and other such gases? What changes is that the linear kinetic energy is still equal to 3/2 R, N times 3/2 R T, and the total kinetic energy is still equal to N C sub Vt, but the linear and total kinetic energy are no longer equal to one another. All right, now that we've put this equation, PV equals 2/3 N times the average linear kinetic energy into some context, however esoteric it might be, I'd like to get on with showing how it's derived. We're going to start by imagining a box with each edge measuring length d. Within this box, we'll have a particle bouncing straight back and forth along the x-axis with velocity v sub x. As it hits the wall, its momentum will change from positive mv sub x to negative mv sub x, resulting in a change in momentum with magnitude of 2mv sub x. Before the next collision with the same wall, the particle will have to go back to the opposite wall in time d over v sub x and come back in time d over v sub x, so the total time between collisions with the same wall will be 2d over v sub x. Now, the average force put on that wall by that single particle then is delta P over delta T, which we found to be 2m v sub x divided by 2d over v sub x, and this all evaluates to m v sub x squared over d. Okay, now it is time to invoke the shape of this box and the fact that the particle isn't hitting exactly the same point over and over again. Some number of particles have been constrained to hit a d by d surface area, and if you had a larger or smaller surface area, the number of particles would scale proportionally. All right, let's think for a moment about my use of the word average a moment ago. I was thinking of the time average force of one particle, we need to average again to consider the average force on that wall by all n particles. Okay, so I went and wrote another equation here, but then I realized this isn't actually an average at all, but a total. But that's easily solved. Look, I've multiplied the formula by big N over big N. So this quantity in parentheses is the average of the square of the x component of the velocity of all big N particles. Okay, now for a rather weird step. We're going to release the particles from their straight back and forth motion and allow, for instance, v1 to be traveling along the vector v1x, v1y, v1z. And of course, v2 is v2x, v2y, v2z. Now the relationship between these components and their magnitudes can be found from Pythagorean theorem. I think we're actually sort of using something called the Equipartition Theorem here. Each particle has a certain amount of energy within it. That energy is distributed about equally between linear kinetic energy in the x direction, linear kinetic energy in the y direction, and linear kinetic energy in the z direction. So what that means as far as our derivation goes is that we're going to replace each of these v sub I x squareds with 1/3 v sub I squareds. 1/3 plus 1/3 v sub 2 squared plus ... plus 1/3 v sub n squared. So that is the total kinetic energy instead of just the, or m, 1/2 m v sub 1 squared would be the total kinetic energy of that particle instead of just the kinetic energy in the x direction. So we got rid of all of the x's and put a 3 down here. We're almost done. There are just a couple of really simple steps left to do. Change the force to a pressure, multiply by 2 over 2, and change the notation for average. Okay, first I'm going to take care of changing the force to the pressure. To change force to pressure, I'm going to take pressure equals force divided by area, which basically just means that I'm going to take the area of one of the sides of the box. So this is d cubed down here. Also, in this same step, I went ahead and replaced v1 squared plus v2 squared plus ... plus v sub n squared with just v squared bar. And finally, I take care of multiplying by 2 over 2, which means that here I'll have 2/3 and here I'll have a 1/2, which puts it into the form 2/3 times n, and this is the average kinetic energy per particle. I will also divide by the d cubed, which can be expressed as volume. So in the end, we will express it as PV equals 2/3 times n times the linear kinetic energy per particle. Now, I put together this table a couple years ago showing the differences in isobaric, adiabatic, isovolumetric, and isothermal processes. You'll find in each case that delta U is equal to nc sub v delta T. That is not what I just proved. What I proved is that the total linear kinetic energy is n times 3/2 r times T. You'll notice here a sort of inverse relationship between the pressure and the work. Work done on the gas is the negative integral of the pressure function. Pressure then, inversely, should be the negative derivative of the work, right? I'd like to see whether I can do yet another one of my most difficult proofs in this same video. The proof of the adiabatic PV curve has frustrated me every semester, as I don't really necessarily cover the material for my class, but I want to be ready to cover it well if the opportunity ever arises. Here is how I usually remember the ideal gas law. It has PV equals nRT, but then it has this extra equality that those things are equal to the internal energy, U, times 2 over the degrees of freedom. In a monatomic gas, the degrees of freedom are 3, one for the x-axis, one for the y-axis, and one for the z-axis, as discussed earlier. Of course, you usually see this as U equals n C sub Vt, where C sub V is approximately equal to the degrees of freedom over 2 times the ideal gas constant. But for this derivation, we're not really even concerned with the nRT portion. We're interested in the pressure and volume relation. Okay, let me make a list of ingredients for this derivation. We already have the ideal gas law and the definition of internal energy. We'll add to that the product rule of differentiation, the first law of thermodynamics, the definition of an adiabatic process, and a whole bunch of steps involving separable differential equations and logarithms. So what I'm going to do here, first, I'm going to take the product rule on that guy there, differentiate it, do a total derivative. It's going to be 2 over degrees of freedom du equals p dv plus v dp. So that's from 2 up there. I use the product rule. Number 3, I'm going to give the first law of thermodynamics. This is written with a lot of different sign conventions, and I'm going to write delta U is equal to, I'm going to just write dq because it's the heat added to a gas, and I'm going to write it as minus p dv. Sometimes this will be written as plus the work on the gas. Sometimes it'll be written minus the work done by the gas, or anyway, it's always minus based on the pressure of the gas is always positive, and the change in the volume of the gas may be positive or negative. And then for 4, the definition of adiabatic, we'll just write dq equals 0. Step 5 is where we really start solving it. So we're going to plug in our minus PdV, because dq is 0, delta U is minus PdV. So 2 over the degrees of freedom times minus PdV equals, then we have PdV plus VdP. And then we're going to do separation of variables and a bunch of logarithms and integration. We got a PdV over here, we got a PdV over here. We can subtract minus 1 minus 2 over df times PdV equals VdP. And that becomes minus degrees of freedom plus 2 over degrees of freedom times PdV equals VdP. I'm going to go ahead and divide by V and divide by P. So we'll have dV over V equals dP over P. And now we've accomplished the separation of variables. I'm going to replace this degrees of freedom over plus 2 over degrees of freedom with gamma times dV over V equals dP over P. And then we're going to integrate both sides. Let's put our integral sign here. And then we're going to integrate it from V sub naught to V and P sub naught to P. So we'll have negative gamma natural log of V over V sub naught equals natural log of P over P sub naught. That exponent comes up here, and we'll write it as V over V sub naught over V. Notice I did the reciprocal times to the power of gamma equals, and then over here, I'll just have P over P sub naught. I could write natural log of both sides, or I could take e to the power of both sides and get this. So now we just multiply by P sub naught over here, P sub naught, V sub naught to the gamma, and equals P V to the gamma over there. P sub naught, V sub naught are, of course, constants, so we can just write constant over here equals PV to the gamma. So earlier, I made the statement that work was the negative integral of the pressure and that pressure was the negative derivative of the work. I'm not currently feeling like that's what I just did. I would say it works in 3 of the 4 cases. In the isobaric, where P is held constant, isovolumetric, where V is held constant, isothermal, where T is held constant. The work on the gas is the integral of the pressure, dV. But in the adiabatic situation, I'm not sure if that integral and derivative relationship works precisely. There are some other questions I have on this topic, like we have this pressure volume space with their pressure volume curves. Is there a similar space involving temperature and entropy? What kinds of parallels would give me a better understanding? Another bunch of questions I have revolve around the Carnot engine cycle. It has 4 processes: an isothermal expansion, an adiabatic expansion, an isothermal compression, and an adiabatic compression. Pretty much all of the engines I know of don't operate this way. I think a steam engine could be thought of like this. The steam comes into the piston at extremely high pressure through a hole. The volume of the piston doesn't grow immediately, but the number of steam molecules does. That hole gets closed off and the piston expands adiabatically until the hole is exposed to the outside air. Now the volume of the chamber decreases at a constant pressure as the air is forced out of the chamber. Now for this steam engine situation, this isovolumetric input comes from steam, approximately 100 degrees Celsius. This isobaric expulsion comes from the air outside, or goes into the air outside the device. So we have a hot reservoir and a cold reservoir for this engine, but here are irreversible processes. The proof for the Carnot engine cycle starts with the assumption of a reversible process. And in general, the descriptions I've heard about the Carnot engines, which involve taking pebbles off and putting pebbles on top of a piston, while either exposing or not exposing the cylinder to a hot heat sink or a cold heat sink or insulation. They don't sound like legitimate representations of any real engine. But for now, I'll leave this video with those sort of open-ended questions and say thanks for watching.